So the work that was described in the previous video was all a matter of helping define what does an atom look like and where are those different subatomic particles. Now, the field of quantum mechanics kind of investigates that. What are those different subatomic particles? How do they interact with one another? And how do they move around? So this idea that if you sent an electric current through a sample and you had this emission of light, you had this movement of these electrons, excitation of electrons going from a low energy level to a higher energy level. Ultimately, that gave way to what was known as the Bohr model for an atom. In the Bohr model for an atom, you have a central nucleus, which is your protons, neutrons, and then outside of that, you have these different rings. Now, these rings are these basically orbitals in which electrons are going to reside. That was a pretty good idea of what an atom looked like and where all these electrons were. Now, what this ultimately kind of relates to, and these different colors that were emitted, relate to the movement of electrons. For instance, going from a high energy or being a high energy electron in one of these outer rings and going to one of these inner rings, well, that's going to cause light to be emitted of a certain color. If you have an electron from one of these inner rings going to a further inner ring, well, then you're going to see light of a different color. So ultimately what that said was the electrons closest to nucleus, sorry, I poorly wrote nucleus there, were your lowest energy electrons, and the further rings were the higher energy electrons. Quantum mechanics is the ability to describe mathematically the motion of subatomic particles and interaction of different subatomic particles. And it has to do with wave functions and the wave-like function of electrons, and ultimately gives kind of a really nice depiction of an atom by showing likely places that electrons can be found. These are also known as probability densities or electron densities. Now, the best way to kind of articulate this, and what Niels Bohr was very helpful in doing, was basically coming up with a series of quantum numbers to show where electrons are. Now, quantum numbers can be characterized by orbitals, and they have specific shapes and energies. Orbitals describe electrons in terms of probable locations around a nucleus, and Niels Bohr came up with these three major quantum numbers to kind of give all of that description. Those quantum numbers, your first three quantum numbers are N, L, M sub L. There's a fourth quantum number, and that's M sub S. That's the magnetic spin quantum number. We'll talk about that a little bit. But these first three are the really maybe the most important ones in terms of identifying where an electron is. So the first quantum number, N, is your principal quantum number. Now, this describes the distance an electron is from the nucleus. And these are always going to have a positive value. They're always going to be positive integers. They're going to be 1, 2, 3, or 4. And they can go on from there. But you would never have, so let me write this out separately. N cannot be 0, sorry, B, 0, or any negative integer, -1 or anything like that. So that's an important point. Now, we'll get into what an N value means in just a little while. Now, the second quantum number, L, also known as your azimuthal quantum number, this is a quantum number that describes the shape of an orbital in which an electron resides. Now, L can have a number of different values. It can range from 0 to n minus 1. So if you have n equals 5, then your L value, and what's important to me and what's really important for you to understand is that the possible values that it could be. If n equals 5, then L could be 0, it could be 1, it could be 2, it could be 3, and it could be 4. L cannot be, well, -1. It could not be 5. Okay, so these are important kind of constraints, and understanding these rules I think is very helpful for you. Now, what these different L values mean, sorry, let me erase this in a second. What these different L values mean is they correspond to a letter that corresponds to a shape of an orbital. So if your L value is 0, the letter that corresponds to is S. If your L value is 1, that corresponds to the letter value of P, 2 is D, 3 is F. Now the shapes here, S is a sphere, P is a dumbbell, D is a double dumbbell, and F is a much more complicated dumbbell series that has multiple dimensions to it. So I'm not really going to get into the shape of those. What I want you to do, however, is maintain an understanding of these different shapes. And we'll get to some examples in just a little while. Okay. Now, your third quantum number, m, more appropriately m sub L, is known as your magnetic quantum number. I mentioned a magnetic spin quantum number, m sub s, a little while ago. Now, in this case, I'm just talking about my m sub L. My m sub L describes the orientation of an orbital in which an electron resides. Now, this can have a value range from L or negative L all the way to 0 to positive L. So, a hypothetical situation, let's say that n equals 3. Then L could be 0, 1, or 2. Okay, now let's take this L equals 2 situation. Let me switch colors. If L equals 2, then what does my m sub L value, what could that possibly be? It could be -2, it could be -1, it could be 0, it could be 1, it could be +2. Okay, so it's important to understand those ranges and those possible values that they could be. Okay. What I'd like to do now is look at some of these quantum numbers and describe some scenarios. So all of these numbers, n, L, m sub L, I like to think about them as coordinates. It's telling you a little bit about where an electron is. These say approximately where an electron is around a nucleus. Okay, so, but let's just talk about the possible rules, or let's talk about the ranges. Could n equal 0? No. N could never equal 0. N equals 1. Is that a possible value? Yes, it is. Okay, so now what we can do is we can say, when we know the value for n, we can say something about what the possible L values are. So if n equals 1, then what are the possible L values? Well, L gives us a definition of L is anything from 0 to n minus 1. Okay, so now let's look back at n equals 1. The only possible value there is going to be 0. Okay, now that's because, well, if n equals 1, then n minus 1 is going to be 0. So the only possible value for L is going to be 0. Okay, so now we can use that and say, what are our possible m sub L values? Our only possible m sub L value is going to be 0, because m sub L gives us a range from negative L to 0 to positive L. Well, now if L equals 0, negative 0 is the same as positive 0, which is the same as just 0. So it's important to keep that perspective on what these possible values are. So now let's say that n equals 4. If n equals 4, then L could have it has several possible values. It could be 0, 1, 2, 3. Okay, so now we would kind of take one of these numbers, one of these values. Let's take 3. If L equals 3, then M sub L gives us a range from -3 to -2 to -1 to 0 to +1, +2, and +3. Okay, so these numbers, it's important now to understand the rules and how, like, one value dictates another value and everything like that. We'll get into the specifics of this in just a little while or in the next video, but for the time being, I hope this is helpful so that you understand those rules. If n equals this, what could L be, and what could M sub L be? All right, well, thank you very much. Have a good one.